Previously we have defined two different frames in order to describe the car's motion. We used a global frame of reference here called N and a local frame of reference attached to the car that moves with the car. We call this one A, and then XA and YA. By looking at the change in orientation between the local frame and the global frame, you were able to determine a relationship between the two coordinate systems given by the parameter theta, which is the angle between the XA axis and the XN axis. And also the angle between the YA axis and the YN axis. We derived expressions for XA with respect to components in XN and YN. And similar for YA. The question for you on the last lecture was to find the derivative of XA hat, and you were able to arrive to the conclusion that the derivative is equal to theta dot YA. And that the derivative of YA is equal to theta dot XA negative. These two relationships will allow us to change from the derivative to the original coordinates again. And we will be able to use these two relationships to find the acceleration of the car in the red coordinate system instead of the black coordinate system. To do so, we can create the description of the position of the red car, the vector RA. For simplicity, let's just call this one R. And later, if we have the two cars, we can rename things. The vector R is equal to R scalar with R equal 16 meters times XA hat. Now if we want to find the velocity, that will be the derivative of the vector R, which is R XA hat dot, and then we can use the relation that we found here to replace and find that the velocity is R theta dot YA hat. Now if we do the derivative again to find the acceleration, which is the second derivative of the vector R, we can compute the derivative of this expression. So R dot is 0, then the derivative is R theta double dot YA hat plus R theta dot and then ya hat dot, and we reuse the expressions we found before to have theta dot square xa hat and then a negative sign here. If you see the expression that we just found, you can identify that the acceleration has two components. One component pointing in the ya direction, meaning along the front of the car, ya axis, and one component pointing in the xa direction, in the xa axis, which is the horizontal direction that is radial or pointing to the center of the track. The negative sign is important because this is a square term, so this is positive. R is the distance, which is also positive, meaning that this vector will always point internally to the rotation. In your physics courses, you have called this term the centripetal acceleration. And now you found an expression for the centripetal acceleration just by derivating the vector description of the position of the car A. Now we will try to do the same thing but using Python and the Sympy physics mechanics library. Let's move this window here so that we have the diagram for the frames of references on hand, and then I will load a notebook where we can write the expression for R with respect to frames of reference. Let's start by importing the libraries. And now let's do the definition of our variables first. We start by observing what are the parameters, the dynamic parameters that describe our system. In this case, it's only theta. And now we have a symbol theta stored in the variable theta. We can compute its derivatives with respect to time, but in order to use the variable t, we have to define the variable. And that's from Sympy, so that we can get theta dot. If we want theta double dot, we can do this. But here we are describing R with respect to reference frames, so we don't need to manually compute theta dot or theta double dot. Let's define the reference frames. So we said that we have a global reference frame, and a local reference frame that is rotating with respect to the global frame. So we define this one with respect to n. let's first check the signature of the function orientNew that allows us to define a frame with respect to another frame. So we have orientNew, the new name, so that will be the name of the new frame, that's A. Then the rotation type, how we are defining the rotation. There are different options. We will always use the one called axis, which is a simple rotation about a single axis. Then we do the amount, so how much it rotates, it's rotating with respect to the original frame, and what is the axis, and that is given as a tuple with the expression and the vector, the direction in which the frame is rotating. So there is a lot of information here, but first let's do A, which is the name of the frame. We are storing that in the variable A. I like to have the names consistent from the name of the variable and the name of the frame. Then we select the rotation type as axis, and then a tuple that will have a value and a direction of rotation. So before we dive into these two variables and define them, I will explain how to obtain directions or axes of your frames. If you have your frame N, you can access the x-axis by do nx, and the y-axis by doing ny as methods. So if I want to create a vector that has 3 units, in this case we are working with meters, so let's say 3 meters in the x direction, in the x coordinate, and then 5 in the y coordinate, you can create the vector this way and observe the vector as an output of your cell in the Jupyter notebook. So it's clear now that we can define the A frame by rotating with respect to the z-axis, the axis that points outside of the paper, that points up, and the value of the rotation is theta, like we defined in our drawing. Please make sure that you understand that there are positive or negative rotations. So if I define my theta this way, I'm rotating counterclockwise on the z-axis, so the angle theta is positive. If I was defining my theta in the opposite direction, meaning that we had our frame defined this way instead, and then this is theta, I would have written minus theta here, or theta in the minus nc axis. That's also an option. So make sure you always identify what are the signs of your angles and in what directions you're doing the rotations between the frames. Now we can do a vector described in the n frame. I forgot one parenthesis. Yep. We have one as the component in the x-axis and one as the component in the y-axis. I can try doing something different here if you want. And now, since we have defined a relation between n and a, because a was produced from n, we can use the option of the method express that the vector has in order to express a vector in different frames of reference. So we can express the vector in the n frame of reference and obtain the same thing that we define here, but we can also express in terms of access from a reference frame. And in that case, we find the exact same terms that we identified before in our previous lecture by doing it manually and observing the angles and the components and the projections to the axis. So you save a lot of time by using this tool because you don't have to keep track of doing components. It will do it for you by using the option or the method express. Now let's define our r vector, and our r vector is 16 meters. In what direction? In the ax direction. That's the most simple way of defining the vector. (16 meters) pointing in the direction of xa. We can transform that into the n coordinate system, into the n reference frame, by using express n and arrive to the previous conclusions we arrived. But we want to compute the derivative of the vector, so we can use diff. This diff is different from a scalar diff because we are differentiating a vector, and we differentiate a vector with respect to a frame. Since we want to know the velocity of the vector by looking from the fixed frame so that we can see the absolute velocity of the car, we will compute the derivative with respect to time from the n reference frame. And this is the velocity vector. I will save it in a variable. We can see that when it computes the derivatives, it expresses them in the n reference frame. But we found that it was more convenient to express in the a reference frame, so I will express in the a reference frame. And you can see that there is a sine square of theta and cosine square of theta that could be factored, and the expression should be more simple. You can do this programmatically by adding the simplify command to the chain of commands of expressions, and then you can see that the velocity is 16 times theta dot in the direction of ay, so pointing along the axis of the car, pointing forward on the car, which makes sense because the car is moving in circular motion along the circular path of the track. Now let's compute the acceleration. I can compute the acceleration by doing the derivative of the velocity with respect to time from the reference frame n, which is our fixed reference frame, and we want to have the absolute velocity and the absolute acceleration of the car with respect to the center of the track. So let's do a vec here to observe the result computed, expressed in the a frame of reference and simplified. And we see that the acceleration has two components, exactly like we found in our analysis here. Let me clear out some of these lines. We have two terms. One term is r theta double dot in the y-axis. That will be the second term in this equation here, this expression. I will copy the equation, the expression for acceleration. I'll copy it here so that we can compare the two terms. we have the centripetal acceleration, and we have the tangential acceleration. And it only took us a few lines of code to create the vector, and then just 2 lines of code to compute the derivative